Good morning, good afternoon, or good evening, depending on where you are, and welcome to the Elenos Group World Broadcast webinar on You've Got Gaps, We've Got Solutions. As always, I'm your host, Chuck Kelly, and I am very pleased to have with me Mr. Perry Priestley, the COO and CSO of Broadcast Electronics, and a very, very knowledgeable person about the digital television industry. Perry, welcome.
Hello, Chuck. Thank you. Thank you for the introduction. Good afternoon. Beautiful day here in just outside of Washington, D.C. It's great to be here.
Lovely here in Indianapolis, Indiana as well. I want to remind everybody, if you have questions at any time during the webinar, you're welcome to type them into the webinar interface. You'll notice a little tab called questions, and you can type in a question there. And at the end of the webinar, Perry and I will do our very best to answer any questions you may have. As always, remember that watching this webinar qualifies for half a credit towards SBE certification under Category 1. So here's what we're going to do today. Here's what we're going to talk about. We're going to, as always, the million-dollar question. We're going to talk a little bit about the Elenos Group and who we are. We're going to talk about what are gaps, actually, and then enter the whole discussion about gap solutions. We've actually expanded the breadth of this webinar, not just talking about translators, but talking about all solutions to gap filling. We're going to talk about translator varieties and theory, on-channel digital repeaters, single frequency networks, and then our complete range of solutions. And then we're going to take your questions. So here's the million-dollar question, Perry. Are you ready?
No.
I understand that our topic today, particularly talking about gap fillers, is extremely timely. Can you tell me why?
Well, yeah, it is very current, actually. There's a lot going on, not just in the United States, but all over the world. There's a global transition to digitization. And so most countries, if they've already implemented digital TV, implement the full power stations. They don't implement the smaller gap filler stations until a second or a third phase. And so that's what you're looking at in many countries now is a second or a third phase where gap filling, ensuring there's a much more robust signal in areas that didn't have great coverage, is actually very, very important. So it's a very current technology, and there's been quite a lot of changes over the last few years in what type of technology is available. So I think it's a good question.
We've got a lot of tools in the toolbox to solve the problem of gaps. Let me just explain for a second who the Elenos Group is. We consist, of course, Elenos, which was founded in 1977 in Ferrara, Italy. A telco manufactures television transmitters, began in 1962 in Orvieto, Italy. Broadcast Electronics in Quincy, Illinois in 1959, and Pro Television Technologies from Denmark, and they have over 50 years of experience. Between us all, we have 60,000 installations worldwide in 130 countries and have over 90 years of experience. So that's who we are at the Elenos Group. And when we talk about bringing various technologies together, we're talking about the combined experience and technologies of these four organizations. So, what are gaps and what causes them, Perry?
Some basic stuff here, Chuck. Terrain, mountains, hills, things that have been there a long time, and the TV station builds knowing full well that they're there and they need to find some way around them or to get over them. Certainly can't go through them. And then, of course, temporary things that have been built maybe after the installation, the transmitter was installed, tall buildings that are in the way. And then, of course, there's some technical issues, such as maybe your horizontal or vertical patterns are not identical. You have a better H or a V coverage, but not the right coverage for certain or specific areas. And of course, then there's just simply areas where you've got two transmitters and they're not strong enough in power, or don't provide strong enough coverage for those areas. There's the gaps.
Yep. And you've shown in this photograph here, or this graphic, an area of Manila, Philippines, and this, whether you have stations on a tall tower in Quezon City, for instance, or over in Antipolo, oftentimes the gain of the antenna causes nulls in the vertical coverage, and then you end up with gaps like what you're talking about. That's just an easy example.
Yep.
All right, so what is in our toolbox that people need to think about that can be used to fill these gaps?
Well, most people, when they think about gap fillers, they just relate to DTS, distributed transmission systems. But there are various ways of doing this, and one of the things here is a list of categories that can be used to actually fill those gaps. And so let me just go through those. There's the basic one where you just simply use a translator. It works on a new frequency, and it transmits the same kind of modulation. An example would be you would be picking up channel 20, you'd transmit channel 20, you'd be picking up ATSC1, and you'd be transmitting ATSC1. A second category would be.
But I got to jump in there.
Yeah, sure.
To make it clear, you'd be receiving on channel 20 and transmitting on channel 23 or something different.
That's right. Yes. If I said that, I didn't say that very clearly, did I? Yeah. So you could be transmitting a different frequency but the same modulation. So that would be category number one. Category number two would be almost identical, transmitting on a different frequency, again, receiving channel 20, transmitting channel 23, but now you could actually be transmitting a different type of modulation. Again, an example, you could be picking up ATSC3 or even say PAL, an analog signal, and transmitting ATSC1 or, as an example, DVB-T2. So different frequencies and different modulation types. Okay. Then a third category, a different type of name, on-channel digital repeater, and we'll be going through this a lot. So the OCDR name, again, this is picking up a frequency, but now transmitting the same modulation, but actually on the same frequency, and that gets complicated, and we'll go into the description of why. So that's the actual gap filler called an OCDR. And then the fourth category, the fourth option, is an SFN, a single frequency network transmitter, and it uses the same frequency. It acts very similar to the OCDR, but in the mode of operation is very different, and we'll go into the description. So picking up the same frequency, transmitting the same frequency.
Okay.
Here's some a pictorial of those options. Translator, you've got a main station, simple receive antenna. Translator demodulates the signal, decodes it, remodulates it, re-encodes it, and feeds it into the amplifier, then a bandpass filter, and then transmits on a different channel. So you receive channel A, you transmit channel B on the same modulator.
Because they're on different channels, there's no problems with feedback, because otherwise it looks like a classic example that would be of an oscillator.
Absolutely, yeah. There is, there's a slight occurrence that if you have a large transmitted signal, channel B, for instance, very high power, and you don't isolate the incoming out, it can overload the front end, even though it's a different frequency. You can overload the front end, but with a relatively simple isolation, keeping one antenna high, the other one low, you can get past that fairly easily. So that's one of the advantages of a translator, is installation is easy, setup is easy, and once it works, it pretty much works for good.
Yep. Okay. How about a converting translator?
Okay, well, the name in itself tells you what it does. It basically converts the signal to a different mode of operation, and you're on a different frequency. So again, as we mentioned, picking up channel 20, now you feed it into the translator, you demodulate it, decode it, and then remodulate it, but remodulate it potentially in a different standard. Again, as an example, you could receive ATSC3 signal and then transmit an ATSC1 signal, feeding it.
And this is actually the new box we were going to introduce today, is a converting translator.
That's right. We do actually have that technology. It's not just a simple regenerative system. It's not what used to be called in the old days a heterodyne system. It truly demodulates and decodes completely down to baseband, allowing you to obtain a lot higher signal to noise ratio, modulation error ratio, much better shoulders, much better performance than it's just a simple regenerative system. So yes, that's one of our new products that we have available in our, as you said, toolbox of tricks.
And a way of looking at this thing is in one transmitter, what you would look at like a rack-mounted transmitter. You've got not only the modulator and the transmitter and the amplifier and the bandpass filter, but you also have a receiver, and that's the key difference.
Yep, yeah, and if you're doing even a basic translator or an on-channel digital repeater or a single frequency network, the quality of the receiver is very, very important. The sensitivity is very important. And there's a few other factors that we'll discuss later on that are key to a decision when purchasing. And you mentioned it there, Chuck, that you've given a couple of presentations on what we call the supercomputer.
Mm-hmm.
And really, at the end of the day, this is what we're talking about. Inside the translator is the Elenos Group supercomputer. We'll discuss that later.
Okay. Let's talk about the advantages of translators.
So one of the main ones is that it's really easy to install. It's very cost effective, usually relatively inexpensive, and it's a great and practical way of filling in gaps. Why is it easy to install? Because you don't really need much adjustment. There's no guard interval adjustment, no interference adjustment. You don't have to synchronize the incoming and outgoing signals. You don't have to do what we'll describe later as echo cancellation. The downside, of course, it does use another channel. And with the world looking at fewer and fewer frequencies for broadcast, obviously channels are becoming more scarce. So there is a downside, but obviously if there is a channel available, a basic translator is truly the optimum performance and the easiest to install and maintain. So that's pretty key.
I would guess that another downside, Perry, might be that oftentimes television stations identify themselves with their channel number. And in the name of the station, I'm channel 3 or whatever it is. And yet when you have a translator, it isn't necessarily channel 3 anymore.
That's absolutely true, and it's a matter of image now. Obviously, in the US ATSC standard, the PSIP, Program System Information Protocol, can be edited in the base information, and you can. But again, it's more of a marketing image. If you're famous for channel 3 or whatever, and the station seems to be picking up channel 26, it can be somewhat confusing to the actual audience. So you're right.
Yep. Okay. All right. Tell us about the on-channel digital repeater.
The OCDR. Yep, it's basically simple thought process: receive channel 20, transmit channel 20. Unfortunately, there's a lot of complicated stuff behind it because simply the isolation between the repeater antenna and the receive antenna is fairly important. They're actually very, very important. We'll go into some quite detail on that later on in the presentation. But OCDR signal is received. It is decoded. There are various algorithms put into place inside the OCDR, and which allows you to, let's say, cancel some of the actual echo effect. And the echo effect is when the actual received channel is actually receiving its own output, its own echo, and that causes obviously some significant problems.
I think anybody who's ever been in front of an audience with a microphone and the speakers behind them understands the problem we're seeing here. We're talking about that channel A input having at most millivolts, but probably microvolts of signal. And within a few feet away is a transmitter on the same frequency with watts of power.
Yeah, that's actually physically a very good example there, because there's nothing more painful than that acoustic feedback that really is unnerving if you actually do that. But that's exactly the same here. You've got you don't have the audio feedback, but you're actually getting RF feedback that's going to cause all kinds of problems if you don't separate the incoming antenna with the outgoing antenna.
And it's actually the classic example or classic schematic of an oscillator.
Yes, an oscillator you don't want. Right.
No, that's exactly right. Okay, so let's contrast what we just talked about with a single frequency network repeater.
So we're going to be doing the same here, receiving the same channel and transmitting the same channel. But this time, in terms of interference, you still obviously have to keep an isolation between the input and the output. But because you have control of your signal, you can synchronize it, you can set the timing, you can now actually really adjust the reception point and the timing thereof of the two signals. So this is a synchronized system, and this is what's really called a single frequency network repeater. Very different to an on-channel digital repeater, although they accomplish almost the same job. So as you can see here, you've got synchronizing signals being fed backwards and forwards between the main station and the SFN transmitter. Now, immediately you should draw the attention that that's a lot more work. You suddenly have to get timing data to every SFN transmitter. And in some cases, that's obviously very expensive, but also not very practical.
Yep. Okay, let's keep looking.
Okay, so SFN advantages. Well, as just like any other on-channel system, it's very spectral efficient because you've got transmitters that you can organize the power and the coverage. You get a much more evenly distributed signal, which is again a nice advantage. Because you have 2 or 3 different transmitters covering certain similar areas, you also have a better availability and reliability. So let's say you lose transmitter B, you can turn up transmitter C and A, and you still got coverage that you wouldn't have with a single transmitter system. So you do have a better availability. It is difficult to implement, and you do actually have to make sure that the transmitters are on exactly the right frequency. And so frequency adjustment is very, very important. And the signals that arrive at the areas which are overlapping have to arrive at the same time. So there's a lot of timing issues that do relate to an SFN. And of course, if you've got transmitters that are covering the same area, the signals must be the same. The actual content, the MPEG stream, must be bit by bit exactly the same. Any difference, and this will cause all kinds of timing issues.
Okay, so what I like about this is there are very few situations in which we as common people get to experience what is the speed of light. But it actually comes to play here. I mean, this is how you figure out where those two signals are overlapping. How can we make sure that those signals are arriving at exactly the same time? The speed of light is important.
Absolutely, yep. I mean, if you look at this picture here, if C and B are not arriving in the coverage area in the middle at the same time, it's going to cause people who are living in that middle part, they're just not going to be able to receive the signal.
Or they'll get messed up signals. Yep.
Yes.
All right, so let's talk about what ends up causing things to be messed up. The main parameters that influence a single frequency network, besides transmitter power and of course antenna location and those sorts of things, are the delay adjustment for making sure the signals arrive at the same time and the guard interval. This is a phrase that most people probably haven't heard, but it's an extra time period which is sent to allow for timing changes. Now we can look at this OFDM spectrum and we can see over a period of time, so this is time, and we're sending out these symbols one after the other, and if we have timing errors that come in and there's no allowance for the guard interval, we end up with problems. So you end up with invalid data. So I've got multiple paths here, and you can see the paths over here. Path number 3 takes longer. So you can see the same symbols are delayed relative to path number 1, which is the shortest path. The television here in the middle is receiving all 3 of these simultaneously. When these are all being read by the receive antenna, you've got this area. In this area, for instance, right here, where you see the pink over it, all are the same. But this area, they're not the same, and that leaves up invalid data, and you don't get the television station. However, if we add a guard interval, that's from a practical standpoint, it's wasted space. It's space where you're not getting your maximum throughput of your data transmission. However, it does allow you to have some jostling room, a little bit of elbow room to make sure that if there are errors, as there are errors, we can still compensate. So you end up with this guard area here and over here. And what happens is when we have these errors from the different path lengths of the different timing, this area is the guard interval, and this area is valid data, and therefore we have a perfect picture, even given the destructive interference, the destructive timing. So let's look at it more graphically, Perry.
Yeah, this is sort of a geographic view of the situation. You've got two transmitters, A and B, and there's a coverage area that's identified by the red lines here. And this coverage area is where you would have to organize, obviously, the timing to be exactly the same where the signal arrives. But it's impossible, if you think about it, to have two signals coming from two different parts to go to many different areas, and this could be many miles across, to arrive at the same time. So
Right.
Obviously, with no guard interval, as you mentioned, Chuck, without a guard interval, you're only going to be able to make some of the people happy some of the time.
Mm-hmm.
So we move to the next thing. So first of all, how do we do the timing? This, as you mentioned, there's two things. There's the timing, and then there's the guard interval. So looking at this is an example of three systems, A, B, and C, just like your previous drawing. And let's say that transmitter A is 6 kilometers from transmitter B, and transmitter A is 12 kilometers from transmitter C. And transmitter A is the main station, it's the generator station. And based on some fundamental propagation speeds, you can calculate that it takes about 20 microseconds to get from A to B and 40 microseconds from A to C. So you'd have to adjust the timing to delay the transmitter number A by 40 microseconds, and then delay the signal on transmitter B by 20 microseconds, and of course there would be no delay on transmitter number C. So you set that all up and hope it works, and obviously they're not going to be identical because there's obviously going to be antenna phasing and directivity. There's going to be things that interfere with the signals differently between A and B and A and C. So there would be some fine adjustment. And it all can be done and all can be organized so that in the interference areas, in the very middle where all three signals are there, you make sure that the signals arrive somewhat close to the exact same time from wherever it came from.
Okay.
And then if you look at the other adjustment, and you mentioned guard interval, so you can put that guard interval, that sort of gap, that space where you're not actually putting any information, and you can make it not so important if in the coverage area. And you can see this red circle in the middle of transmitter A and B, and that indicates what you would be, where you'd put the guard interval. So during that space, you're not going to have any problems. Unfortunately, maybe, though, all the people are where those red blocks are.
Murphy's Law.
Yeah, exactly. So then you actually would adjust the guard interval timing a second time, in a sense, to move it. And if you move to the next slide, you can actually just move it slightly to the right. Now, again, as I mentioned, you can't make all the people happy all of the time unless you significantly increase the guard interval. But there comes a point to the compromise where, you're actually going to have zero payload. Everybody gets coverage, but there's actually no content. So it's going to be a compromise between payload and guard interval size.
This is why the RF propagation analysis is so important, because what you're trying to do is move those overlap zones, those interference zones, to places in general where people aren't. You do that by figuring out the power of the transmitters, by figuring out the location of the antennas, what kind of antennas, what kind of patterns. So you can solve part of that way, and the rest of it can be solved with this technique.
You're absolutely right. But you did emphasize something that's quite important there, Chuck, that there's a lot of work to determine all that. You've got to get everything exact, and it really has to be exact in terms of timing and frequency.
Okay. So
what do you need to make an SFN system? Of course, you need an SFN transmitter or a repeater, but there is also other components that generate the BTS, the broadcast transmission system generation, like the encoder. You need a distribution network, whether it's via fiber or microwave. You need something, obviously, to insert all those delays. You need, obviously, the modulator, and then you need some kind of synchronizing system. And then on top of all of that, you need methods of measuring the timing and synchronizing the system. So for an SFN, it truly is, when it's set up properly, very effective, but setting it up properly is also quite an engineering feat, in a sense.
Okay.
OCDR again, on-channel digital repeaters. Now, it's the same as an SFN repeater, but it has a couple of key differences. Let's look at the disadvantages first. Let's just summarize the situation. The disadvantage of an OCDR is that it is limited by the echo. In other words, the larger or louder that feedback is from the transmitting antenna to the receive antenna is going to significantly reduce the capability of the power you can transmit. So a key issue here is you may go out and buy yourself a 500 watt OCDR system, but when you connect it all up, you don't have the right echo cancellation system, you don't have the right isolation between input and antenna and transmit antenna. You may only get 1 watt out of it. I mean, it may be that extreme. Obviously, the transmitted quality, because you're not decoding it down to a baseband and then re-encoding it, remodulating it, is going to be deteriorated. So as you do hop to hop, there will be reduction in quality. Depending on the quality, how you can overcome that. There are various issues and techniques, and we'll actually get to that a little bit later. The advantages, I think, in most cases outweigh the disadvantages. It doesn't require an additional transmit network, so you're not connecting all the stations together with synchronizing pulses and timing information. It certainly makes installation a lot easier. It's a lot lower cost because there's a lot less equipment to purchase. And of course, the data is all synchronized with a GPS in a single SFN, and there's no GPS required in an OCDR.
Yep. Let me clarify this just a little bit. In an SFN, the input signal is coming from microwave or satellite or whatever it is. It's another path coming to this transmitter. And then you do all the synchronization stuff, and so that it all looks right in the overlap zones. In an OCDR, it's actually a receiver inside the box that's receiving this other station and retransmitting it on the same frequency.
Yeah, that's a good description there, Chuck. They're, in a sense, they're accomplishing the same job, but they're actually doing it in a very different way.
And because of this magic wand called interference cancellation, you can overcome some of the disadvantages of OCDR. And let's see about why.
Yeah, that's a key aspect there. So here's just a little chart to explain some of the terminology more than anything else. We've got 2 graphs on the right-hand side, and then some descriptions. You've got an echo delay, which is the delay it takes from the main signal to the actual receive signal. Then you've got an echo window. Here you've got three additional signals. Signal number 2, for instance, would be along a echo window, and that may be from a mountain that's 10, 20 kilometers away. You've got number 3 here, the blue pulse. That's the reflection potentially from a nearby building. And then in the middle of that is reflection number 4, and that could be from a moving object like a truck or a car or so. Those will be varying in height and strength. And the distance between the main receive signal and those echo signals are called the echo window. And of course, one last important measurement is the strength of the signal that you're able to transmit versus the strength of the signal that you receive, and that's called the echo ratio. So those are 3 important terms that you should understand and know about echo cancellation and on-channel digital repeaters.
Let me just because this is so important and critical to what we're talking about, let me kind of repeat it in my own terms
Yeah,
and
please.
just make sure it comes out. So this is the input signal coming in from the other station that you're receiving. This is your retransmitted signal, which is, of course, much stronger because it's coming out of your transmitter, which is on location. Then
Yep,
you have various echoes that come from other places, and the further away they are, the further in time they are spaced from the original station. And
perfect.
the echo ratio is the difference between the, the retransmitted signal and your original signal that came in. Okay? All right.
Spot. Yes, perfect. So this is a quick summary of why echo cancellation is actually very, very important. The diagram here, there's a complicated formula, but it's actually not that complicated. You've got what's called the system transfer function, or I, of the echo cancelling system, and that's related to gain. It's related to the isolation between two antennas, which is labeled here as E. And Z, or Z, is another function that's basically the phase change or the phase relationship between the receive antenna and the transmit antenna. The certain things you can't really change. The gain is a fairly fixed situation. Z, the phase relationship, is fixed. The only thing that really is something that you can change, and that is the level E isolation. So as you increase E, or in a sense decrease it because it's in negative dBs, as you increase that, of course, you improve the performance of the OCDR. And so E is critical in terms of the operation. And of course,
I can give you a real world example of that. Many, many, many years ago, don't ask me how many, but many, many years ago, I worked as a chief engineer for some radio stations in southwestern Colorado. And one of the places we had a translator was on the top of a place called Cavernous Mountain. And there was an organization that was repeating, that had translators for television that were repeating stations received from Albuquerque, New Mexico, on channel. But what they did is they had the top of this mountain, and the receive antennas were down the side of the mountain pointing towards Albuquerque, and over on the other side of the mountain, separated by the mountain itself, were the transmit antennas. And the transmitter shack was right at the top, and it had long cables that went down to both of them. That's increasing your system isolation.
That really is the best way. There's nothing more, I think, tenuous than a big mountain in the middle. So that will definitely give you some significant isolation. But that's obviously the perfect situation. That's obviously the best way to do it. Not always available. You don't have handy everywhere a nice mountain to put the antennas either side of. But
Exactly.
that is the ideal situation. And of course, I'll just go back one little bit. I didn't mention this. Of course, when you've got the formula here that's GEZ plus this other GEZ. This other GEZ is actually the signal that's being fed back. Mm-hmm. And that signal you need to get rid of. You don't want that echo. You don't want that feedback. And so there is a technology called echo cancellation, and it's shown here in this little orange box. Get the mouse here, and it's shown here. And this is taking a feedback sample and feeding it back and into the so that you get this sort of negative feedback system that allows you to cancel the actual echo. The better this system here, the less interference you're going to have, and the less interference you have, the higher the power you can have. And let's examine that a little bit more in detail. But echo cancellation here, very, very important.
In a sense, this is very much like adaptive pre-correction.
Yes, absolutely.
You're taking a sample of the output, comparing it with what you want, and then separating out the part you don't want, which is that feedback, and inserting it back in the input stream out of phase, but very carefully.
Yep. Yeah. Okay. Opposite in amplitude and phase. Yep. Obviously, this is all done in the RF domain, so it does get quite complicated. But with the right filtering, with the right organization of the structure of the system really can make a difference. And let's get into some examples. So here's an example of echo cancellation with or without ICS. ICS is the integrated echo cancellation system. So just take some simple, the received signal, let's say, is minus 50 dBm. You were able to obtain a pretty good antenna isolation between the input and output of 80 dBs. You have about a 10 dB gain in the transmit antenna. So you deduct that 10 dBs away from the antenna isolation to get to about 70 dBs. So you've got a total isolation of about 70 dBs. Now, the maximum power is obviously your receive signal, minus 50 dBm, plus that 70 dBs, and you get an output of 20 dBm. 20 dBm isn't much. It's 100 milliwatts. And even, as I mentioned earlier in the presentation chart, that even if you buy a 100-watt transmitter, but this is your configuration, the maximum power you'll get from that transmitter is 100 milliwatts.
Yeah.
So now let's see what ICS or echo cancellation can do for you. Same scenario, 50 dBs of receive signal, antenna isolation about 80, antenna gain of 10 dBs, but this time with the correct ICS, with the correct echo cancellation system, let's say you can get up to 30 dBs, and that's what I believe we've been getting. In fact, I heard reports of up to 40 dBs of some of the tests that we've been doing on our latest echo cancellation system. You add those numbers to the system, and of course you get the same results. 80 minus 10 is 70, but now you actually add the 30 dBs of echo cancellation. You now got 100 dBs. Now you add the 100 dBs to your minus 50 dBm, and look what you got is 100 watts. If you had 40 dBs, for instance, of echo cancellation, you would have a kilowatt. So now it's real significant coverage. Now this is equivalent radiated power, because this is the power that's transmitted from the antenna, but a kilowatt of power is certainly a lot better than 100 milliwatts if you're trying to get a robust signal into certain areas that you're really trying to target.
Exactly. Okay. So all of this is made possible by this RF supercomputer that we keep mentioning, which is basically a modulator developed by Pro Television Technologies, part of the Elenos Group of companies located in Copenhagen, Denmark. And in this box, which has 2,200 components and a 16-layer PC card, it's basically a programmable computer with an RF output. It can create any signal, including all digital and analog television standards. It can even do radio, FM. But in this one box, because all we have to do is to change the program we're feeding it, that is the instruction set, the firmware that is going on to this card. It can be an exciter, a transmitter, a translator, a converting translator, an SFN, and it has all the automatic computing for the SFN, or an OCDR. All can be built in to that card. So it's the magic wand. It's the RF supercomputer that fixes everything. And it's got an incredibly powerful, well, I guess this is necessary. Anytime you have something that is so configurable, you have to have a user interface that allows you to get into it and change everything. So in this situation, you can take any one of these boxes and drag it down to here and then make the adjustments. So it's very graphical, and you can reconfigure a system from being an OCDR to an SFN translator of any standard, ATSC translator, ATSC3 translator. All these things can be built and controlled and modified even at a distance, because this is a web interface. So if you've got the internet there, you can log in with your web browser and make changes on the go.
Absolutely. And the slide, and it's my fault, only says ATSC, but of course it's just as configurable for DVB-T as well as ISDB-T. So the international standards works as a gap filler, works as an on-channel digital repeater, and of course works as a transmitter or a translator. So flexibility beyond most people's dreams.
And the wonderful part about it is it used to be that when you change a standard, for instance, going from ATSC the legacy version that we're using today to ATSC3, the new version that's coming online, you started all over again. You bought a whole new box that did that. But this one, you changed the software load, and now you're in ATSC3.
Yep, absolutely. And the software load, I've done it myself, literally takes just about 10 to 15 seconds. So it's not like this is a big effort as well. So I mean, stations could even consider being ATSC during the day and ATSC3 at night.
Yeah.
Knows. Lots of opportunities there.
Okay, so what the bottom line of all this is we can help. The Elenos Group has the answers that you need. We provide optimal performance by a transmitter on any frequency, different frequencies, i.e. a translator. If that's not available, if you can't use a different frequency, then an OCDR can provide excellent low capital cost, easy installation, low cost of ownership. A single frequency network repeater is an option for an excellent choice for the right conditions, and especially that you have all that ability to have a separate, basically an STL. And any choice is basically a click away with the Elenos Group Digital Exciter Translator, OCDR, SFN, RF supercomputer. And we can handle your needs, VHF or UHF, from 1 watt to 7,200 watts or more.
In a single cabinet. Yeah, the list is getting so long, Chuck, between what we can do these days. It's actually difficult to remember all the options and all the variables that's available all in the same box. I must admit it's difficult for our salesmen to look after this, but they are here to help, and they certainly can help you configure and make the right selection between whether you need a OCDR, an SFN translator, or just a simple transmitter.
Yep. And this would be the time for the questions, but we don't have any. We've done a pretty darn good job of handling them all. So we're going to actually be out on time today. If you end up with questions you'd like to ask and you didn't get an opportunity to type it into the interface, feel free to send us an email. And I'm ckelly@bdcast.com. Perry, you are?
p.priestley@elenos.com. I think you've got a list of email addresses.
Yeah, but I don't have us on there.
Okay.
Everybody else. This is the sales team that you can contact depending on your area, and they will be more than happy to get the answers for you. They may not know everything that you ask, but they can sure find out. And again, the 4 companies: Elenos, Broadcast Electronics, Atelco, and Pro Television. Perry, thanks. This has been fun, and I hope helpful and useful for people.
I hope so too. Thank you very much for the invitation again, Chuck. I really appreciate it.
And you can find out our upcoming webinar schedule at www.elenosgroup.com/webinar. And answering the one question that as always on everybody's lips, yes, this webinar is being archived, recorded, and will be available to you from this same webpage, elenosgroup.com/webinar. And you can watch it. If you've missed part of it or whatever, you can watch it there. Thank you, Perry, and thank you, listeners. And this concludes our webinar for today. Thanks, Perry.
Thanks, Chuck. Bye-bye.
Bye-bye, all.